Alright, we are into chapter 3 because chapter 2 was short, and this chapter can be a little abstract, meaning difficult to visualize, um, because it's the study of electrons in the atoms and where the electrons are located and how they behave. Um, because a lot of stuff deals with, in chemistry, deals with bonding and how bonds are made or through electron transfer or electron sharing. So we gotta focus on where the electrons are located and how they affect the atom and their properties. So the first one is understanding the simple electronic structure of a atom, basically the Bohr method. It's simple, it's not the method of now, but it's the first understanding of what's going on with an electron in an atom. So you have basically principal quantum shells, so energy levels. And energy levels are determined by where they are on the periodic table. The first row is E1, the second row has 2, the third row has 3, and the fourth row has 4, and so on. And obviously, as you go further in energy levels, you get further away from the nucleus, and you can hold more electrons once you get into higher energy levels. So, um, you can see the further out shells, more electrons have energy-wise because it takes um, more energy to move, um, and they're held less tightly with the nucleus because they're further away from the protons. Positive protons and negative electrons basically are trying to make an attraction, and the closer they are to the nucleus, the more the radius or diameter is smaller. Here's the number of electrons they can hold up, and again, easy way to remember is counting on the periodic table. Energy level 1 is 2, energy level 2 is 8, energy level 3 is 18, and it goes 32. It's basically the row on the periodic table. So, for example, lithium arrangement is pretty simple. It has 3 electrons total, 2 in the first energy level because of hydrogen and helium, and then they have 1 on the outer shell. That's because they are in the first column. Neon has a full outer shell. It has 2 because of the first 2 elements, hydrogen and helium, and then holds 8 all the way from lithium to neon in the outer shell. It's full. So chlorine, a halogen, um, acts like all the halogens. It has 7 in the outer shell. Missing 1 electron. Here, how you can see a table. How you can see that hydrogen is the only one that has a 1 in the outer shell because helium is 2 electrons. So all the first shell is always full except hydrogen. And then as you go across the periodic table, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and then sodium has all 8 in the outer shell. And then sodium will have 1 extra in the third shell because it's the start of a new energy level. So, here's a question. Write the simple electronic configuration of the following atoms. Sulfur is in the third row. It goes 2, 8, 6. Magnesium, same row as sulfur, 2, 8, 2. Fluorine has a full outer shell and then 7 across, so it's 2, 7. Potassium would be 2, 8, 8, and 1 because it's start of the fourth row. And then carbon is in the second row and 4 over from lithium, so it's 2 and 4. Remember, the number of electrons has to equal the atomic number. if it's a neutral atom. All right, part 3.2. Um, the evidence of electronic structure, so more elaborate. Um, so the first is the most important part of a bond is the ionization energy. Now, an ionization energy is basically how much energy it takes to remove an electron. They're easily removed in metals, remember, because they become positive. A little more difficult in nonmetals because they want electrons, so it's hard to remove electrons. So it's the element's energy needed to remove one electron from an atom in 1 mole of atoms of an element in the gaseous state. And the reason why I say gaseous state is because they have to be completely excited to easily remove electron. Um, so it's excitement, high energy. Um, that electron is easier removed at that state. So here's calcium. It's in the fourth row, so it has 4 energy levels. You can see 1, 2 in the center, then 8, 8, and then 2 more in the outer shell. So 1 electron leaves, that's the first ionization energy. An easy equation, calcium gaseous yields Ca plus 1 gas phase plus 1 electron because it leaves. And it doesn't require much energy, 590 kilojoules per mole. Now, a second electron leaves. Okay. So you're starting at Ca plus 1 now and yield Ca2 plus an electron. What do you think happens to the energy required to remove a second electron? Would it be greater or less than the first? If you said greater, you are correct. And the reason why is because of the protons in the nucleus. You remove electron, that means there's more now protons compared to electrons. So there's more positive charge bringing in the radius. So the energy level actually shrinks a little bit, and you have a tighter radius. So it takes a little more energy to remove that electron. Now, if you take a third electron, bye-bye, from a full energy level, 8 electrons, your equation would be Ca2 plus. Again, you remove an electron, so it becomes Ca3 plus. What do you think the ionization energy would be? It would be greater or less than the second ionization energy. And again, the pattern shows it's going to be greater, and it's a lot greater. You're almost 5,000 kilojoules per mole compared to 1,100 from the second ionization energy. So, why is that big jump between the second and the third? And that's because it has a full energy level. After you remove 2 electrons, calcium, the fourth energy level is gone. So the third energy level is full with 8 electrons, and again, that's noble gas area. And we know noble gases are very stable. So to remove that extra electron takes a lot more energy to break apart. And again, the radius becomes smaller. The bond between the protons and the electrons now becomes stronger, and you need more energy to break apart that electron. Here's a table. You can see a big thing you want to look at is the jump between energy levels. If you look at lithium, 519, remember lithium is in the first column and jumps all the way to 7,000 because after 1 electron it has a full outer shell. Same thing with beryllium. You take away 2 electrons, there's a big jump to the third, just like calcium was. Boron, same thing. You take away 3, big jump after a full energy level. Carbon's the same thing. Nitrogen, big jump between 5 and 6. Oxygen, big jump between 6 and 7. Fluorine, big jump between 7 and 8. Okay, so once you get into a full shell, it takes a lot more energy to remove that electron. You go back to sodium, there's a big jump between 1 and 2 because sodium is just like lithium. They're going to be 1 electron in the outer shell, easy to remove. So once they get to a full outer shell, then it takes a lot more energy. Okay, so you notice that it's going to be between 1 and 2 is a big difference. Between 2 and 3, huge difference. So why such a large difference between these two ionization energies is because of that outer shell. Once you get to a full shell, it takes a lot more energy to remove. So it's easy to tell where on the periodic table an element is based on their ionization energies. Closer an electron removed to the nucleus, the more energy required. Oops. Sorry. And that's again because of that tighter radius between the electrons and protons to cause more attraction, so it takes more energy to remove that attraction. So you can see here you have a full outer shell after removing 2 electrons. You have 2, 4, 6, and 8. Full shell. It's very content, very happy, so it takes a lot more energy to break apart. Alright, so back to that table. As a new electron is removed, what happens to the ionization energy? Obviously it becomes larger because of that bond between the attractiveness between the protons and now the electrons. So the ratio is off. You have more protons now than electrons, so you have a more tighter attraction. So some trends. It always increases for each new electron removed. The ion charge gets bigger, causing a greater attraction between the protons and electrons, so it's harder to remove those electrons. Big jump between successful ionization energies, meaning between energy levels. So that's how you tell where it is on the periodic table, is with that big jump after it's full. After you take away electrons to a full energy level, then you take a lot more energy to remove that electron. So look at nitrogen. You have 5 electrons in the outer shell. Same cell, so they're very, does increase a little bit because of the attractionness between the protons and electrons. But if you look at 6 and 7, the jump between 5 and 6 is huge because they are in different shell. They're in the first energy level. 1, 2, 3, 4, and 5 are in the second energy level. So count protons. You have 5, 2 in the center, first shell. Oops. So you can see those 5 electrons. Once you get rid of those 5, you have the new energy level. So you can see that big jump between 5 and 6. Alright, first homework question is to write the equations, just like I did for calcium, removing electrons. So the first ionization of calcium, so that means it removes 1 electron. The third ionization energy of potassium, so it removes 3 electrons. The second ionization energy of lithium, it removes 2. And the fifth ionization energy of sulfur, so it removes 5 electrons. Alright, factors do influence the ionization energy. Obviously the size of the nuclear charge. So as the atomic number increases across the row, the ionization energy increases because it has more protons. More protons means more positive charge, so you have more attractiveness towards the electrons. Distance of outer shell from the nucleus. As the distance from the nucleus increases, the ionization energy decreases because they're further away from the protons. Further away meaning there's less force there, so it's easy to remove those electrons. And the shielding effect of the inner electrons. As the full electron shell increases, the ionization energy decreases because outer electrons feel less attracted to the nucleus. So it's kind of the same as distance of outer shell, but you have a full electron shell because it's going to go towards the outer electrons. Here is a graph. You can see from the example, you can see the ionization energy obviously increases as the number of electrons removed. That's because of the protons' attractiveness, again, towards these electrons are increasing. More protons compared to less electrons, more force holding on to the electrons. You can see a big jump right here between 9 and 10. Okay, that's because after that you have a full shell, so it takes more energy to remove. Here's an example. Again, you have 11 protons, so it's sodium. You have a full outer shell, so this one electron here in the outer shell is easily removed, but it gets harder and harder to remove because of that full second energy level. Alright, so you have a ionization energy of boron, first, second, third, fourth, and fifth ionization energies. Why is there a large increase between third and fourth ionization energies? So between here you have 3,600 and 25,000 kilojoules per mole. And the big reason, again, after you remove 3 electrons, you have just 2 more electrons in the outer well, it'd be the first shell because the second shell is gone. So once you're a full shell, full energy level, again, it takes a lot more energy to break apart because they're fine, they're happy, they're great. They have full shell, they're awesome. Alright, explain how these figures confirm that the electron structure of boron is 2-3, meaning that it has 2 electrons in the first shell and 3 in the outer shell. So you can look at the third energy level. It takes 3 electrons to remove to make a full shell of 2. So that confirms that the big jump is between the third and fourth, and that will show that it takes 3 electrons to remove. Alright, here we have an unknown element, and it asks for which group in the periodic table does this element belong to. Group 1, Group 2, Group 3, so forth to Group 8. So you're looking for a big jump. So you study the numbers, 1,000, 20, 3,000, 3,000, 4,000, 7,000, 8,000, up, it goes up to 27,000, then 31. So you see there's a big jump between 6 and 7. So that means it took 6 electrons to remove to get to a outer shell. So that means it would be group 6, which would be oxygen. So this could be something in oxygen group. Couldn't be oxygen because oxygen only has 8 electrons. So it could be sulfur or something like. Alright, homework question. So the first ionization energies of an element are 1,090, 2,350, 4,610, 6,220, 37,800, and 40,000. 47 should be 47,300. Which group in the periodic table does this element belong to? And explain your reasoning. Alright, last section 3.1. Subshells and atomic orbitals. So this is pretty mind-blowing. Probably the abstract part of atomic structure. So we'll go over this again in class, but this gives you an idea of what we're going to go over. So you have principal shells, energy levels, 1, 2, 3, 4. In those shells, you have different subshells, which are based on where electrons are located. And each of those subshells are broken down into orbitals, which are specific where electrons are located. So you can see there's a progression, simple, a little more specific, and then very specific where the electrons are located. Here are these subshells, and you can see there's some overlapping. You have your energy level 1 with a simple 1s. You have energy level 2 with broken apart into a 2s and a 2p. The third energy level is broken up into 3s, 3p, and a 3d. The energy level 4 is 4s, 4p, 4d, and there's also a 4f, which we'll get to. Alright, the subshell, they're called orbitals, are broken down into these lobes, they call them. Each lobe holds 2 electrons, one in opposite spins. They call them spins, opposite directions. So this p orbitals, you can hold 6 electrons. 1, 2, 3, 4, 5, 6. In the 2s, you can hold 2 electrons. In the d, 2, 4, 6, 8, 10 electrons. Mind is blown. Okay, so the energy of electrons increases as you get into the bigger shells. The maximum electrons can hold in the S is 2, and the P is 6, the 10 is for D, and F has 14. After argon, subshells do not necessarily fill in the SPD order. Starting with potassium, subshell order overlaps, and we'll get to that. So how the shells fill. You have energy level 1 is just an s orbital, holds 2 electrons, hence hydrogen and helium. Energy level 2 holds a total 8, which is broken down into an s and a p. 2 in the s for lithium and beryllium, and then 6 in the p for boron through neon. Energy level 3 does the same thing, 2, 6, and then 10 for the transition metals. So you can see here, 2s, or 1s, sorry, 2s, 2p, 3s, 3p. Notice 4s is underneath 3d, and that's because of the potassium row. Then you get to 3D, and that's where you get to the transition metals. Okay. Each subshell contains one or more atomic orbitals, SPD. Um, and each orbital can only hold a max of 2 electrons. Uh, the outer region around the nucleus can be occupied by 1 or 2, which a max can hold 2. Here is some picture of the other orbitals again. So that means in this px, the x means it's on the x axis, the y axis, and the z axis um, can hold 2 electrons each. That's why the p's can hold 6. 2, 4, 6. Here's some other diagrams of the lobes. You draw in like a circle for S. The p's are like a affinity sign, just in different axes, x, y, and z. Here's some more diagrams of the orbitals. Here your alkaline earth metals, because they hold 2 electrons. Here are your p's for 2, 4, and 6. Your d's for your transition metals. Again, 2, 4, 6, 8, 10. And then here's your f's of the lanthanide series. 2, 4, 6, 8, 10, 12, 14. So you always start with the lowest energy, which is 1s. And it fills first and follows by an order of energies. And you basically follow along this diagram. So you write your s's first, 1s through 7, 2 p's, your d's, your f's. And you just follow the order. So it goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. Alright, name the 3 types of orbitals present in the third principal quantum shell, so the third energy level. So looking on the chart, you have n equals 3. So the 3 types of orbitals will be your 3s, 3p, and 3d. State the maximum number of electrons that can be found in each subshell of the third quantum shell. So remember the 3s, S can only hold 2 electrons, the p can only hold 6, and the d can only hold 10 max. S orbital is 2 electrons, the p orbital is 6, and the d orbital is 10. Mind is blown. We will continue this again in class. Just make sure you